Hello friends, welcome to another lecture on sampling. In this, we will continue with the impulse train sampling, and specifically we will look at ideal interpolation and the sampling theorem. Recall that a sampler converts a signal from continuous time to discrete time. In impulse train sampling, we multiply the continuous time signal m of t with a periodic impulse train delta ts of t, and that results in the sampled version of the continuous time signal. In frequency domain, we note that this multiplication operation becomes convolution that results in the original spectrum m of f appearing at all integer multiples of the sampling frequency fs. That means we get infinite copies of the original spectrum m of f, each centered at the integer multiple of the sampling frequency fs, and each copy of this spectrum is scaled by a factor of 1 by ts. Pictorially, if we assume m of t to be a band limited signal, band limited to w hertz say, then the spectrum of the sampled signal is the same spectrum m of f repeated at the integer multiple of fs. So fs, 2fs, 3fs and so on this side, minus fs, minus 2fs and so on. And these frequencies are w minus w. This frequency is fs minus w and so on. We saw in the previous lecture that if we use a low pass filter here, if we pass the sampled signal through a low pass filter whose cutoff frequency is greater than w but less than fs minus w, in that case we can recover the original spectrum and therefore the original message signal m of t. As far as this scaling 1 by ts is concerned, we can take care of it by having the gain of the low pass filter as ts. So what we find that it is possible to recover the original message signal from its samples if this frequency fs minus w is greater than this frequency w, the maximum frequency of the message signal. So we saw it in the previous class that fs minus w must be greater than w for perfect recovery of the original message signal from the samples, and which implies that fs must be greater than 2w. That is, the sampling frequency must be greater than twice the maximum frequency of the signal, which is w. This very important result is known as the sampling theorem. We will formally state it in a few minutes. Let us look at this operation mathematically. Let's assume that first we'll see it in frequency domain and then in time domain. Let us assume that we have an ideal low pass filter h of f with the gain t of s in the frequency interval between minus fs by 2 to plus fs by 2. In short, we can write it as mod f less than fs by 2, and it is 0 elsewhere. So if we pass the sampled signal m delta t through this filter, we say that we will get the original signal m of t from here. Or in frequency domain equivalently, we can write that if m delta f is given to this filter, the result will be m of f, the original spectrum. It is fairly easy to see in frequency domain as m delta f multiplied by hf. And what is m delta f? M delta f is 1 by ts summation k from minus infinity to plus infinity m of f minus kfs into what is hf? Hf is this ts in this interval and it is 0 otherwise. For mod f less than fs by 2 and it is 0 otherwise. Now in this interval k can only take one value, which is 0, right? For other values it will go beyond this interval, and therefore what we get is, for this ts and this ts will cancel and we get m of f. Now because k is no more appearing there, this summation becomes redundant and we just get m of f. So it's very easy to see that when the sampled signal is passed through an ideal low pass filter, we get the original signal back. This is what we have shown in frequency domain. Now what happens equivalently in time domain is very interesting, and let us now look at that. So once again, let us write m of f equal to m delta f into hf. And let us now take the inverse Fourier transform. When we take inverse Fourier transform, m of f becomes m of t, right, in time domain, and m delta f is m delta t. The multiplication becomes convolution, and h of f, let us write it, the inverse Fourier transform as h of t. Now what is m delta t? M delta t, we know it is summation n from minus infinity to infinity m of n ts into delta t minus n ts, which is an impulse train with the strengths of impulse equal to the message values at the sampling instants, and thus convolved with h of t. Now what is h of t? That is the question. How to obtain this h of t? So come back to this slide and note that this h of f is equal to ts. It's a constant in a given frequency interval and it is 0 otherwise. So basically it's a rectangular function. Let us recall here that if we have a function, rectangular function, or let's do it separately. Recall that if we have a rectangular function in time domain, say from minus capital T by 2 to plus capital T by 2 with height 1, this function we denote by rect T by capital T, and it's a standard function for which we know the Fourier transform. The Fourier transform for it is given as capital T sinc f. Now using the duality result, we know that if we equivalently have a rectangular pulse in frequency domain, say from minus fs by 2 to fs by 2 of height 1, this is of course written as rect f by fs, that is a rectangular pulse of height 1 with fs centered at the origin. Then if we take its inverse Fourier transform, the time domain function would be a sinc function whose expression will be fs sinc fs into small t. Now in our case, this hf has an amplitude of ts. So if in place of this amplitude 1, if we have the amplitude as ts here, then this expression in time domain will be multiplied by ts using the scaling property of Fourier transform, because Fourier transform is linear, so it is additive as well as homogeneous, and therefore it follows the homogeneity or scaling property. So we get this as the time domain expression. And now because fs is 1 by ts, ts into fs, this is equal to 1. And therefore what we get is sinc fst. So if we are calling this as h of f, then this is h of t. Okay, so h of t is sinc fst. So let us put this value here. So it is sinc fst, and now we use the convolution property of the impulse function, that if a function is convolved with a shifted impulse, we get the shifted function. And we get here summation n from minus infinity to infinity m n ts sinc fs, and replace this t by t minus nts. So t minus nts, or we can write it in a simpler manner as summation n from minus infinity to infinity m nts sinc fst minus fs n fsts, and fsts is 1, so it is simply n. This result is called the ideal interpolation. It's a remarkable result. It says that if we have infinite sinc functions, each shifted by n on fst axis, or each shifted by ts on small t axis, with the amplitude, main amplitude as m of nts, the message value at the sampling instance, then the sum of such infinite sinc functions would exactly be the original signal m of t. And this result is known as ideal interpolation or sinc interpolation or band limited interpolation. Interpolation means to obtain a continuous time signal from its samples. Let us try to see this pictorially. Suppose this is 0th instant. So we have the sinc at t equal to 0. Then this is 1 by fs, which is equal to ts. From this expression, you can see fst, since fs, the sinc function will have 0 crossing values at fst equal to plus minus some integer m, so t will be m by, so 0 crossing will be, so if I talk about 0 crossings for the sinc function, it will be fst equal to plus minus m, or t equal to plus minus m by fs, or plus minus mts, because 1 by fs is ts. So I have this as fs, this will be 2ts, 2 by fs, or 2ts, and so on. Similarly, this will be minus t, this will be minus ts, and so on. So this way, if we have such infinite sinc functions with main amplitudes as the sample values of the message signal at sampling instance, m of 0 here, m of ts here, and so on, m of minus ts here, then such a summation of infinite sinc function will exactly give the original message signal m of t, provided, what is the condition? Provided that the sampling rate is greater than 2W, or equivalently 1 by fs is less than 1 by 2W. And what is 1 by fs? 1 by fs is nothing but the sampling interval. So if the sampling interval is less than 1 by 2W, or equivalently the sampling frequency fs is greater than 2W, then it is possible to perfectly recover the signal from its samples. And this is precisely what is called the sampling theorem. It is formally stated here. So the sampling theorem for strictly band limited signals of finite energy can be stated as follows. From the transmitter's perspective, it can be stated as a band limited signal of finite energy, band limited to W hertz, can be perfectly represented in terms of its samples if the sampling interval Ts is less than 1 by 2W. And at the receiver side, from the receiver's perspective, the sampling theorem can be stated as a band limited signal of finite energy, band limited to W hertz, can be perfectly recovered from its samples if the samples are taken at a rate fs greater than 2W hertz. Now, what about this equality? This is an interesting question that we'll discuss in some other lecture. It is important to note that fs is called the sampling frequency, whereas Ts, 1 by fs, is called the sampling period. 2W is called the Nyquist rate, and 1 by 2W is called the Nyquist interval. So that's all for this lecture. Thank you.